Hey everybody, this is Corey and Victoria. We are the Professors Du Bois, and in this video lecture we're going to talk about electron configuration using the spdf notation.
That's right. So we've been talking about these quantum numbers, and the quantum numbers give us the address, right? So it gives us the orbital that the electrons are in. And so we've been thinking about just one electron at a time. So we're going to be looking at the entire picture now. We're going to look at the atoms, all the electrons in an atom, and we want to know what the atomic structure is. So we need to know what all the electrons are and where they're housed and what these orbitals are looking like, their size and shape. So each electron has 4 quantum numbers, and that's the address. But the electron configuration is going to represent all of the atom's electrons. The first 2 quantum numbers, N and L, give us the type of electron, like 1s or 3p. And we're going to continue on with that and build an entire electron configuration.
So here's our final quantum number. This is quantum number 4. This is m sub s, and this is the spin of the electron. So it turns out that electrons actually generate a magnetic field. So, if you think about a magnet, it has like a magnetic north pole and a south pole. Well, it turns out there's 2 different spins an electron can have, or 2 different ways the electron can have like a north pole. So we designate this with +1/2 and -1/2. I'm not sure why it's a half, but this is the value that goes into the this address for the m sub s. It's either +1/2 or -1/2, and it depends on which I want to say end, but it's not even an end like a magnet, but we have a north pole depending on where the north pole is.
Right.
In that magnetic field.
So the first 3 numbers define the orbital, and then since 2 electrons can be in each orbital, then the m sub s tells us, which electron it is. So as we're going through this orbital filling, so how these orbitals are filled with all of these electrons, we're going to be using these rules, and we'll bring them up as we need them to fill these electrons and build this electron configuration.
We should note, though, that the Pauli exclusion principle is kind of of utmost importance right now, because we just talked about the spin, and since each orbital can hold 2 electrons, electrons are negatively charged, and you would think they would repel each other within that orbital, but because of this spin, they are allowed to exist in the same space.
Right, and we do want to remember that we have 1s orbital, 3p orbitals, and 5d orbitals, and that's going to keep coming back.
That's your L value.
Over. Yep.
Okay, so for a single electron atom, this is hydrogen. It's the only single electron atom. The energy levels really just depend on n, and you can see here that n equals 1 is the lowest energy level, and as n gets bigger, the energy gets greater, so energy on the y-axis. And one thing to note is that the s orbitals, the p orbitals, both have the same amount of energy as long as they're the same n. And we're going to see some differences here when we get to multi-electron atoms.
When we have multi-electron atoms, we have repulsion between the electrons. So since we have more than 1 electron, they're all negatively charged, we can have some repulsion, and that changes the energy value. And the energy then is, the energy of the orbital is n plus L instead of just n. And we have some interesting things going on, and I want to move forward and then come back to this and show you what we mean. So we can see how the 2p is of greater energy than the 2s, and so on. So some generalizations here. So as n increases, the orbital energy increases for the same type. So that's comparing these together. So 1s is lower energy than 2s, etc.
So what we mean by type is the orbital, it's an s orbital or it's a p orbital.
Right. So as L increases in the same n, then the energy also increases. So we're comparing, say, 3s, 3p, and 3d. You can see how the energy is increasing as L is increasing.
Yeah, so L goes from 0 to 2 in this case. 0 for s and 2 for d, 1 for p.
Very good. And as n increases, we know that we've learned that the energy difference between the n gets smaller and smaller and smaller as you get further and further away from the nucleus. And when this happens, they are very, very close in energy, and we get some overlapping. So that's where, look at this, we have 3s and then 3p, and then 4s is of lower energy than 3d. And we need to know where these energy levels are so that we know when we can fill these with electrons, because electrons fill with lower energies first. So we'd fill in this order. So we need to know what this order is.
So we can basically, use this n plus L and talk about how only 2 electrons are in an orbital, and we get a filling order, and it's great. And here it is down below, but very, very difficult to memorize, because you can see how it isn't numerical. It is numerical, but the numbers don't increase. It isn't simple.
It's not logical.
We have a much simpler way to do this. Hang in there.
Right. And you might have learned some different ones in high school, and you can use any way that you've learned that works for you. This is what works for us. We like this. First of all, I'm going to take helium and put it right over here. That helps first. You want to walk us through this?
Sure. So the way I like to think about assigning electrons is it's kind of like reading a book, and the periodic table is my book, and I'm going to start at the upper top or the upper left, and I'm going to read left to right just like I'm reading a book. So my lowest n is 1, and you can see I'm in the s block of elements. So we're going to have a 1s, and there's going to be 1 electron for hydrogen. This doesn't have hydrogen written in, but we all know hydrogen is atomic number 1. So there's my electron configuration for hydrogen, 1s1. So I can use the periodic table to guide me through this. So helium, I can say, okay, the n number is 1, and so I have 2 electrons that can go in that s orbital. So I'm going to call this 1s2. And there's your electron configuration for helium. Simple. So let's go to lithium. Lithium is n equals 2. Well, lithium has 3 electrons. So the first electron, there's going to be 1 electron in the 1s orbital. There's actually going to be 2 because there's 3 total, and the lowest energy fills first. So this electron configuration is going to be 1s2, and then the next lowest energy orbital is the 2s orbital, and that's going to be 2s1. And we can see that just by reading the periodic table. See that? Like, you might not have known that 2s was the next lowest, but if you just read the periodic table like a book, you will you'll be able to do this. Let's do something like carbon. So we've got carbon over there, and this is in the p block, and we're going to use these blocks. So carbon has 1, 2, 3, 4, 5, 6 electrons. I'm going to teach you an electron counting trick in just a second. So we're going to start at the upper right. We've got 1s2, that orbital's full. And then we have 2s2, that orbital's full. That accounts for 4 of the 6 electrons. So where do we go next? Well, we're still in period 2. So it's a 2p, and we have 2 electrons. Now notice if you count left to right in that p block, this would be this would be a p1, this would be a p2, this would be a p3, p4, p5, and p6. But we were specifying carbon, 6 total electrons, and that is 2p2. So if you look at those superscripts, those represent the numbers of electrons. So I can just count those. If I'm given an electron configuration, I can simply count those to determine the total number of electrons and therefore the identity of the element.
So we can continue on and read this. As long as you know where your blocks are, you can read right to left and just keep going.
Now it gets
4s, 3d, remember
Right.
that's 3d, 4p, 5s, 4d, 5p. Now be careful right here. These, remember, are right here. So after 6s, it goes to 4f. Remember, these are 4f. N is period minus 2. 4f, and then we have, let's see, 3, 4. We have 5d, and then 6p, down to 7s, 5f, to 6d, 7p, and that's your filling order.
So you have to include all of those as you go. You end where your element ends. So hopefully there's a shortcut or a trick when you get down toward the bottom of the periodic table. So if we look at beryllium with 4 electrons, we can just start reading the table, right? We have 1s1, 1s2, and then the s is full. It only holds 2 electrons. And so I drop down to, to n equals 2 or period 2, and I have 2s1, 2s2, and there's a total of 4 electrons. There's beryllium, there's the electron configuration. For oxygen, same approach. We're going to have the 1s2, we have 8 total electrons, 2s2, that s will only hold 2, and we go to the p. And so we need a total of 8, we have 4, this is going to be a 2p4. Oh, look at this, this is scandium. 1s2, 2s2, got 4 electrons. 2p6, and if you had the periodic table handy, you could count across there are 6. And then we'd go down to 3s, and that'll hold 2. How many do we have total now? 6, 7, 8, 9, 10, 11, 12. Got a long way to go. And then right over to 3p, that'll hold 6. I'm up to 18, 19, 20, 21. 4s will hold 2. Now we're into the transition metals. So it's a 3D, right? That's a D block with transition metals. I think I needed 3 there. 1? Really? Scandium?
Right.
Well, let's count. We can check.
Let's
2
check.
and 2 is 4, and 6 is 10, 12, 18, 21. You're right. Scandium, 21 electrons. And I got that by just counting those superscripts.
Right. Here's some practice for you. So we want you to write the full spdf. Sometimes that's called the complete electron configuration for the following elements. Pause the video and give it a shot. Here's your answers.
Wow, that tellurium looked like a real monster.
It sure did. I hope we have a trick to make those a little shorter.
I'm sure we do. Stay tuned.
Yep.
There's a trick.
There's a trick. Come back and watch the next video for the trick on how to not have to write these big, long electron configurations. So glad you joined us. We'll catch you in the next one. Bye-bye.